Hi class, let's do an example video on confidence intervals. We'll do our first one on proportions. So I have a question here, right? It says domestic cats kill many more wild birds in the United States than scientists thought, states a recent article. Researchers used a sample of n equals 140 households in the US with cats to estimate that 35% of household cats in the US hunt outdoors. Find and interpret a 95% confidence interval for the proportion of household cats in the U.S. that hunt outdoors. Okay, so if you ever get confused on what you're trying to do, the last sentence always has what it is that we want to figure out. Okay, so the first thing that I like to do for confidence intervals is I like to state the things that I know already. Okay, so for this video, I'm going to keep everything in printed font instead of handwriting everything out because my handwriting is atrocious on the tablet that I have. So these are the things that we know. Okay, I did not really have to calculate anything here except for Q hat. All of this stuff is coming from my word problem, right? So if I read through my word problem once or twice, I notice that it tells me these things, right? It tells me I have a sample size of 140. I have a success rate, which is in this case cats that hunt outsides, of 35%. My Q hat, which is the complement of P hat, 1 minus P hat, is 65%. So 65% of cat owners in the US out of this sample did not have cats that hunted outside. And then the last sentence is find a 95% confidence interval. So my confidence level, CL confidence level, is 95%. Okay, the next thing that I need to do is I need to state the conditions that I know. Okay, so what that means is we tend to use the central limit theorem, the CLT, when we do confidence intervals. In order to use the CLT, I need to make sure I have the conditions in order to use the CLT. Okay, so let's think about this for a second. If I want to drive to my friend's house, there's a few things that I have to have first, right? I have to have a car, I have to have insurance, I have to have a driver's license, I have to have a friend, and I need to have gas in that car, and I have to have my car keys. If I don't have any of those things, I can't drive to my friend's house. Okay? Similarly, if I want to use the central limit theorem, there are certain things that I have to have. Okay? The first of those things that I have to have are randomness. If I don't have randomness, then I can't assume that I have a good sample. If I don't have a good sample, then I can't use that sample to talk about my population. Okay, next I have to have independence. So in order to be independent, I need to have a small sample from a large population. That keeps me, I can assume that none of the households that I contacted in my survey and asked them about their cats, they probably don't know each other because in the United States, it's very large. There's a lot of people that have cats, and if I sampled randomly 140 people, it's highly likely that there is no influence from one person that I surveyed to the other. Okay, so I have to make sure that all of my data values were collected independently of another, that there is no influence from one collection to the other. Okay, and the last thing that I have to have is normality. If my distribution is not normal or approximately normal, then I can't use the central limit theorem. I can't talk about a distribution of means. All of that is based on using normal distribution, inverse norm, normal CDF, all of those things. If my distribution is not normal, I can't use the tool that I have for calculating probabilities and critical values. Okay, so when we're talking about proportions, the way that I assume normality is that my sample size times my number of successes, or my expected number of successes, has to be more than 5, and my expected number of failures has to also be more than 5. Normally we would use the true proportion here, but I'm trying to guess the true proportion. I want to have a confidence interval that captures the true proportion. So I'm going to use the next best thing, which is the proportion that I got from my sample, right? So my sample had a success rate of 35%. That should be close to the true value of P, assuming that I have a nice sample, right? If it's nice and random, it should be representative of the whole population. So I should be able to use this P hat to get a good approximation for the exact value of P. And this confidence interval is really just going to be used to kind of narrow down, you know, how far I would expect P to differ from my sample value that I got. Okay, I can start to do some calculations now. So let's look here. The first calculation I can do, the easiest one, is to figure out my alpha level. Okay, my alpha level is just the complement of my confidence level. My alpha level is basically the probability that I'm wrong, right? So if I want to make it so that I have a 95% confidence level, well, I'm 5% not confident. Okay, the next easiest thing to find after I find alpha is half of alpha. Okay, this half of alpha value is going to be used for me to find my z-score that I need to use in my calculation. So I find alpha first, and then I cut that in half, and that's my alpha over 2 level. Once I have my alpha over 2 level, I can find my critical value, okay, the z-score that goes with this area, right? So z of alpha over 2 is z of 0.025, so I throw that into inverse norm, and this is basically saying on the left side tail, if I have this area with the standard normal distribution, this is the z-score that I get, okay? So we normally use the positive value of this, or the right tail, so we'll change this to a positive 1.96. Okay, the next thing that I need is the standard deviation for the distribution of proportions, okay, for this normal distribution, this distribution of proportional values. So I need to find my standard error. That is the standard deviation of means, the standard deviation of proportions. Here we're using a proportion, right, P hat. So I need sigma of P hat, which follows this value, this formula. If I plug everything in, I get 0.0403. Okay, now I'm ready to do some calculations with this. I have my standard error, I have my critical value, my z-score, and I have my P hat. So I can throw all of that together to find my confidence interval. P hat plus or minus the z-score times my standard error. So I just plug in the values that I've calculated one at a time. And when I plug these in, I'll get out 0.2710 and 0.429 as my values. Okay. Therefore, my confidence interval for P, the true proportion for this problem that I was asking about, should be between 0.271 and 0.429. We always put the smallest one first and the largest one last because it's an interval. It's from this value to this value, so the smallest one goes first. Okay, generally from here we would draw a graph of our distribution. However, I'm going to save this one for maybe the next video that I do. But you would just draw the normal distribution and you would make sure to label all of the values that we just found, right? So I would label my P hat, I would label my standard error value right below that, and then I would label this value and this value on either side of that graph and shade the in-between area and say that that is 95%. Okay. After we find our graph, we have to write a conclusion because if all I have is an interval, that doesn't really tell me, the reader, anything, right? So remember, generally what you're going to be doing is you're going to be answering a question like this for a boss. You're going to be writing a report. You're going to be reading a report or some sort of journal or scientific paper. So it's important that there is a summary there for what just transpired, right? So our conclusion is that we are 95% certain that the true proportion of house cats in the U.S. that hunt outdoors is between 27.1% and 42.9%. These two values as percentages because this is a distribution of proportions, so 35 is a 35%. So we want to write this into proportions and put it into context for the reader.